There's something humbling about standing beneath a sky full of stars, isn't there? That vast, endless expanse above us, stretching farther than our minds can grasp, holds secrets that have captivated humanity for millennia. But what if I told you that every shimmering light you see is more than just a distant sun? Each one is a chapter in an epic story, a story of discovery, perseverance, and revelations that reshaped our understanding of the universe. Welcome to Celestial Chronicles, the untold legacy of cosmic discoveries and their impact, a journey through the moments when humanity dared to look up and question everything. Think about the last time you marveled at the night sky. Maybe you spotted Orion's belt or traced the arc of the Milky Way. But behind those familiar constellations lie tales of forgotten pioneers, visionaries who cracked the codes of the cosmos centuries before telescopes or satellites. These weren't just scientists, they were storytellers, philosophers, and dreamers who saw patterns in the chaos and dared to ask, what else is out there? Their breakthroughs didn't just advance astronomy, they rewrote history, influenced art, inspired religions, and even sparked revolutions. The stars, it turns out, didn't just light up the night, they lit up the human imagination. So why does this matter now? Because every time we uncover a new cosmic truth, it's like finding a missing piece of a puzzle we didn't even know we were solving. From the ancient astronomers who mapped the heavens with nothing but naked eyes to the modern-day revelations about black holes and dark matter, each discovery ripples through time, changing how we see ourselves and our place in the universe. And here's the thrilling part, we're still writing this story. The cosmos hasn't finished surprising us, so let's embark on this adventure together, through triumphs, controversies, and mind-bending mysteries, to uncover how the stars have shaped not just the sky above, but the world beneath our feet. The universe is waiting to share its secrets. Are you ready to listen? Long before the first telescope pointed skyward, humanity was already writing its name among the stars. Picture this, a Babylonian scholar crouched under the open desert sky, etching careful notations into a clay tablet as Jupiter drifted between constellations. Or a Mayan priest high atop a pyramid, calculating the precise return of Venus as a sacred calendar unfolded. These weren't just stargazers, they were the first astrophysicists, armed with nothing but patience, ingenuity, and an unshakable belief that the heavens held patterns worth decoding. Take the Babylonians, who meticulously recorded planetary movements for over 4 centuries. Their star logs, preserved on cuneiform tablets, reveal something astonishing. They'd unlocked the cyclical nature of lunar eclipses, predicting them with eerie accuracy. No lenses, no satellites, just the human eye and a relentless dedication to pattern finding. Meanwhile, halfway across the world, the Mayans wove celestial events into the very fabric of their culture. Their Venus tables carved into stone weren't mere charts, they were bridges between the divine and the earthly, aligning ceremonies with the planet's 8-year cycle. But here's what's truly remarkable. These ancient breakthroughs weren't lost to time. Centuries later, when Copernicus dared to suggest Earth wasn't the center of the universe, he stood on the shoulders of those early skywatchers. Their data, their methods, even their mistakes became stepping stones for the scientific revolution. That's the hidden thread connecting an astronomer in ancient Babylon, jotting down Jupiter's path to the Voyager probe now drifting beyond our solar system. The same insatiable curiosity, the same drive to map the unknown. And let's not forget the tools they invented. The astrolabe, crafted by Islamic scholars in the Middle Ages, traces its lineage back to the star clocks of ancient Greece. Even Stonehenge, with its stones aligned to solstices, whispers of a time when architecture itself was a cosmic calculator. These weren't primitive guesses, they were precision instruments born from generations of observation. So why does this ancient wisdom still matter? Because every time a modern telescope captures light from a galaxy billions of years away, it's fulfilling a promise made by those first stargazers, that the universe is knowable, one observation at a time. Their legacy isn't just in the stars they mapped, but in the audacious idea that humanity could read the sky like a book. And as we'll soon see, that book was only just beginning to reveal its secrets. History often remembers the loudest voices, but the cosmos whispers its truths to those who listen most carefully. Among them was Caroline Herschel, a woman who defied 18th-century expectations to become astronomy's first professional female scientist. While her brother William built telescopes, Caroline stood beside him, not as an assistant but as a peer, discovering 8 comets and cataloging nearly 2,500 nebulae and star clusters. Yet for decades, textbooks reduced her to a footnote, as if the night sky itself hadn't etched her name among its wonders. Then there's Subramanian Chandrasekhar, a young physicist who boarded a ship from India to England in 1930 with a radical idea. He calculated that dying stars could collapse into unfathomably dense objects, what we now call black holes. The scientific establishment mocked him. One Nobel laureate publicly dismissed the theory as stellar buffoonery. But Chandrasekhar's equations were unshakable. Decades later, when telescopes finally glimpsed the shadows of black holes, the universe proved him right. His story isn't just about perseverance. It's a reminder that truth isn't decided by consensus, but by the relentless pursuit of evidence. And what of Henrietta Swan Leavitt? A Harvard computer, one of the women paid pennies to analyze photographic plates of stars. She noticed a pattern in the flickering of certain stars called Cepheids. Their pulse revealed their true brightness, a key that unlocked the scale of the universe. Edwin Hubble used her discovery to prove galaxies existed beyond our own, yet Leavitt's name rarely appears beside his. These pioneers shared more than brilliance. They faced barriers, gender, race, institutional bias, that tried to silence them, but the cosmos doesn't discriminate. Light bends the same way for everyone. Today, when the James Webb Space Telescope peers into the infancy of galaxies, it builds on the work of those once overlooked. Their legacy isn't just in what they found, but in the doors they pried open for others. So the next time you gaze at the stars, remember, the universe's greatest discoveries weren't handed down from on high. They were wrested from the dark by curious minds society too often ignored. And as we continue to explore, who's to say which of today's unsung researchers might hold the next cosmic revelation? The stars keep their secrets well, but they reward those who dare to look, no matter who they are. Imagine living in a time when questioning the heavens could land you in prison. That was the reality Galileo Galilei faced when he trained his telescope on Jupiter in 1610 and saw moons orbiting it, proof that not everything revolved around Earth. Overnight, his observations shattered a worldview held for over 1,000 years. But this wasn't just about astronomy. It was a battle for the soul of knowledge itself. The Church's geocentric model, inherited from ancient thinkers like Ptolemy, wasn't merely scientific doctrine, it was divine order. To suggest Earth moved around the sun wasn't just incorrect, it was heresy. Yet Galileo, armed with nothing more than a tube of glass lenses, gathered evidence too compelling to ignore. His sketches of lunar craters and Venusian phases didn't just challenge ideas, they exposed a universe far stranger and more dynamic than anyone had dared to dream. The backlash was swift. By 1633, the aging astronomer knelt before the Roman Inquisition, forced to renounce his findings under threat of torture. But here's the twist: even as Galileo murmured his recantation, legend claims he whispered under his breath, and yet it moves. Whether he actually said it or not, the sentiment endured. Truth, once seen, couldn't be unseen. What makes this moment pivotal isn't just the science, it's the precedent it set. Galileo's trial became a rallying cry for intellectual freedom, proving that evidence could outweigh authority. Ironically, the very institution that silenced him later catalogued his manuscripts, preserving them for future scholars. By the time the Vatican formally acknowledged its error in 1992, Galileo's heresy had become the foundation of modern astrophysics. This clash echoes today whenever new discoveries unsettle entrenched beliefs. From Darwin's evolution to the detection of exoplanets, progress often walks hand in hand with controversy. Galileo's story reminds us that understanding the cosmos isn't just about telescopes and equations. It's about the courage to let observation guide us, even when it leads where power fears to tread. The stars, after all, owe no allegiance to earthly doctrines. They simply shine, waiting for us to see. Newton's revelation didn't begin with a flash of genius, it began with a question. Why did the moon hang in the sky instead of crashing down like an apple? That simple curiosity led to a revolution. In 1687, his Philosophiae Naturalis Principia Mathematica unveiled a radical idea. The same force pulling fruit from a tree also kept planets in their orbits. Gravity wasn't just a local phenomenon, it was the invisible hand shaping the cosmos. For the first time, humanity held a universal key, a set of equations that could predict everything from tides to trajectories. But Newton's brilliance lay in more than his conclusions. He gave us a method, a way to see the universe not as a chaotic mystery, but as a grand, calculable machine. Take his laws of motion. When a comet streaked across the sky in 1680, astronomers panicked, calling it an omen. Newton, armed with his principles, traced its path and declared it would return. 76 years later, Halley's comet reappeared right on schedule, proving the heavens obeyed predictable rules. This wasn't just science, it was a declaration that the cosmos played by laws we could learn. Yet even Newton knew his work was incomplete. "I have seen further by standing on the shoulders of giants," he wrote, acknowledging the astronomers before him. His own equations couldn't explain why gravity worked, only how. That gap would haunt scientists for centuries until Einstein reimagined gravity as the curvature of spacetime itself. But here's the beauty of Newton's legacy. His laws weren't overturned, they were expanded. Just as a telescope's lens sharpens an image, each generation refines our cosmic understanding. What's often overlooked is how these ideas transcended science. Newton's clockwork universe influenced philosophers like Voltaire, who saw in it proof of a rational, orderly world. Composers like Handel wrote music mirroring celestial harmony, while architects designed buildings with proportions reflecting planetary orbits. Gravity became more than a force, it was a metaphor for connection, a reminder that everything, from atoms to galaxies, is bound by unseen threads. So what cosmic laws still hide in plain sight? Perhaps the answer lies in the dark matter we can't see but know must exist, or the quantum quirks defying Newton's orderly rules. The universe hasn't stopped whispering. Every time a probe slingshots around a planet using his centuries-old math, or a student solves a physics problem with F equals ma, Newton's truth endures. The cosmos speaks in equations. And if we listen closely, there's always more to hear. The universe has a way of humbling even the sharpest minds. take Fritz Zwicky, the sharp-tongued astronomer who peered at the Coma galaxy cluster in 1933 and noticed something impossible. Those galaxies were whirling around each other at breakneck speeds so fast that the combined gravity of all their stars, gas, and dust should have sent them flying apart. But they held together as if clutched by invisible hands. Zwicky, never one to mince words, dubbed the missing mass Dunkel Materie dark matter, a placeholder name for a cosmic ghost that would become one of science's greatest riddles. Fast forward nearly a century, and we've mapped dark matter's fingerprints everywhere. It bends light around galaxies like a cosmic lens, a phenomenon called gravitational lensing. It sculpts the universe's vast web-like structure, guiding galaxies into clusters and filaments. We even see its shadow in the afterglow of the Big Bang, etched into the cosmic microwave background. Yet for all its influence making up roughly 85% of all matter in existence, dark matter remains stubbornly invisible. It doesn't emit, absorb, or reflect light. It doesn't collide with ordinary atoms. It's a cosmic specter felt but never seen. So what is it? Theories abound. Some physicists propose WIMP, weakly interacting massive particles, hypothetical heavy particles left over from the universe's fiery birth. Others favor actions, ultralight particles streaming through space like an intangible breeze. There are even wilder ideas, that dark matter is primordial black holes formed in the first chaotic seconds after the Big Bang, or that we've misunderstood gravity entirely and need new physics to explain these galactic anomalies. Here's where the mystery twists. Dark matter isn't just missing mass, it's the architect of everything we see. Without its gravitational scaffolding, galaxies would never have clumped together in the early universe. Stars wouldn't ignite, planets wouldn't form. We owe our existence to this unseen force, and yet every attempt to catch it in the act, from detectors buried deep in mines to particle colliders smashing atoms, has come up empty. The harder we search, the more elusive it becomes. Perhaps the most tantalizing clue lies in the Bullet Cluster, two galaxies colliding in distant space. When astronomers mapped it, they found something eerie. The visible matter, slowed by the crash, lagged behind. But the gravitational lensing effect, the warp of spacetime caused by mass, raced ahead, as if most of the cluster's weight had slipped through the collision like a ghost walking through walls. That mismatch is dark matter's calling card. It doesn't behave like anything we know. What if dark matter isn't one thing, but many? Some theorists suggest a whole, dark sector of particles interacting through forces alien to our own. Others imagine dark atoms, dark stars, even dark galaxies, a parallel universe woven seamlessly into ours, felt only through gravity's faint tug. The possibilities stretch the imagination, but that's the thrill of the hunt. Every null result, every failed experiment narrows the path toward revelation. One thing's certain, solving this puzzle won't just fill a gap in our equations. It'll rewrite our cosmic story. From the tiniest particle to the grandest galaxy cluster, dark matter's secrets are woven into the fabric of reality itself. And when we finally pull that thread, the universe might unravel in ways we can't yet dream. Einstein's universe didn't tick like a clock, it breathed, stretched, and twisted. Picture a trampoline sagging under the weight of a bowling ball. Now imagine that warp isn't just bending space but time itself, slowing seconds near massive stars like cosmic molasses. That's the heart of relativity, a revelation that upended everything we thought we knew about reality. When Einstein published his theory in 1915, even fellow physicists struggled to grasp its implications. Newton's laws had ruled for centuries, but here was a universe where light could curve, twins could age differently, and the fabric of existence depended on your speed. Take something as mundane as your phone's GPS. Without relativity, it'd guide you into a ditch within minutes. Satellites orbiting Earth experience time slightly faster than we do down here, thanks to gravity's weaker pull at altitude. If engineers didn't account for that tiny discrepancy just microseconds per day, your location would drift nearly 6 miles off within a week. Einstein's math isn't abstract. It's the reason your ride share arrives on time. Then there are black holes where relativity's weirdness crescendos. At their edges, known as event horizons, gravity grows so intense that not even light escapes. Time doesn't just slow, it stops from an outsider's perspective. A clock falling in would appear to freeze, its ticks stretching into infinity. Yet for the doomed observer crossing the horizon, nothing seems amiss. This isn't science fiction. It's what equations predict and telescopes now confirm, like the first image of a black hole's shadow in 2019. But here's what even Einstein doubted: gravitational waves, ripples in spacetime itself, born from cataclysms like colliding neutron stars. He assumed they'd be too faint to ever detect. A century later, in 2015, LIGO lasers caught a wobble, a billionth the width of an atom, from two black holes merging a billion light-years away. The universe had literally jingled like a struck bell. What's astonishing isn't just relativity's accuracy, but its resilience. Every test, from atomic clocks on jets to the bending of starlight during eclipses, has only cemented its truth. Yet Einstein himself wrestled with its implications. His famous, spooky action at a distance, quantum entanglement, clashed with relativity's cosmic speed limit, light's velocity. Even now, reconciling relativity with quantum mechanics remains physics' Everest. So what's left to discover? Maybe the true nature of singularities, where space-time curvature becomes infinite. Or whether wormholes, cosmic shortcuts, could exist without collapsing. One thing's certain: relativity didn't just change how we see the universe. It taught us that reality, at its core, is far more malleable and mysterious than anyone imagined. The cosmos isn't a static stage, it's a living, twisting dance of space and time. And we're only beginning to learn the steps. Edwin Hubble peered through the 100-inch Hooker telescope in 1924, expecting to see more of the same, stars clustered within our Milky Way. Instead, his observations revealed something astonishing. Those faint smudges of light weren't part of our galaxy at all. They were entire islands of stars, other galaxies, drifting in the unimaginable vastness beyond. And when he measured their light, he uncovered an even stranger truth. Nearly all of them were racing away from us. The universe wasn't just big, it was stretching, growing, as if space itself were breathing. This wasn't just a shift in scale, it was a revolution in thought. Until then, even Einstein had assumed the cosmos was static. But Hubble's data showed something radical. The farther a galaxy was from us, the faster it receded. The numbers told a story. Space wasn't merely containing galaxies. It was expanding between them, carrying them apart like raisins in rising dough. That single observation rewrote cosmic history. If the universe was growing, then rewinding the tape meant everything must have once been crushed together in an unfathomably hot, dense state. The birth cry we now call the Big Bang. Yet Hubble's discovery raised questions as profound as the answers it provided. If space is stretching, what is it expanding into? The mind recoils at the idea. We're used to things having edges. A balloon inflates into a room, after all. But the universe might not need an outside. Imagine an ant on the surface of that balloon. As it expands, the ant sees every point on its surface moving away, yet there's no center, no boundary. The universe could be like that, finite but unbounded, growing without expanding into anything. Here's where it gets stranger. In the 1990s, astronomers found that expansion isn't just continuing, it's accelerating. some mysterious force dubbed dark energy is pushing galaxies apart faster and faster. If this keeps up, distant galaxies will one day vanish from view, their light stretched beyond detection. Future civilizations might look up and see only darkness, their night sky devoid of any evidence that other galaxies ever existed. Hubble's revelation didn't just change textbooks, it redefined our place in the cosmos. We're not at the center of anything. We're riding a speck of stardust in an ever-growing ocean of space, part of a story that began nearly 14 billion years ago. And that story is still being written, one retreating galaxy at a time. In the vast silence between stars, a small golden disk drifts, carrying the essence of humanity across the cosmic ocean. The Voyager Golden Record, attached to both Voyager probes in 1977, isn't just a time capsule, it's a handshake stretched across light years, a fragile bridge to civilizations we may never meet. Imagine being part of the team tasked with summarizing Earth's entire story in just 90 minutes of sound and 115 images. What do you include? A baby's cry, the crackle of a thunderstorm, Chuck Berry's Johnny B. Good. The result was a mosaic of life, painstakingly curated by Carl Sagan and a diverse committee who debated everything from Bach to Bulgarian folk songs. But the record's true brilliance lies in its universality. Without words, it had to speak in a language any intelligence might grasp: mathematics. The cover bears a pulsar map, a celestial roadmap pointing back to Earth using the rhythmic beats of dead stars. Even the instructions for playback are etched in symbols, a stylus binary code and a diagram showing how to spin the disk at the right speed. It's a message that says, we're here and we tried. Now consider its journey. Voyager 1, the farthest human-made object from Earth, crosses interstellar space at 38,000 miles per hour. Yet in 40,000 years, it will merely graze the next star system. The odds of it being found are astronomically slim, but not zero. That's the poignant beauty of the Golden Record. It wasn't sent because we expected a reply. It was sent because the act of reaching out matters as much as the reach itself. What would aliens make of our selections? The laughter of a child, the crashing waves, or the EG patterns of a woman in love, these aren't just data points. They're fragments of a species that dreams, creates, and wonders about its place in the dark. The record's final track, a haunting hour-long recording of Earth's brainwaves, ends abruptly, cut off mid-thought, as if to say the story isn't finished. Perhaps that's the legacy of the Golden Record, not as a message to others, but as a mirror for ourselves. It captures a moment when we dared to cast our voice into the void, not knowing if anyone would ever hear. And in that act, we discovered something profound. The universe feels less lonely when you call out into the night, even if no one answers. Armstrong's bootprint on the lunar surface may have been solitary, but it carried the weight of an army. Behind that iconic moment stood legions of engineers, mathematicians, and technicians, many of whom history nearly erased. Take Katherine Johnson, the black physicist whose orbital calculations were so precise that John Glenn refused to launch until she personally verified the computer's numbers. Or Margaret Hamilton, the software genius who coined the term software engineering, as she coded the Apollo guidance system by hand, stacking printouts taller than she stood. When the lunar module's computer overloaded minutes before touchdown, it was her fail-safes that prevented disaster. The true scale of this collaboration staggers the imagination. Over 400,000 people worked on Apollo, from seamstresses stitching space suits to cafeteria workers feeding round-the-clock teams. Even the astronauts' wives formed an unspoken sisterhood, smiling for cameras while privately calculating the odds their husbands might not return. The space race wasn't just rockets and flags. It was midnight shifts in windowless rooms, families uprooted for desert test sites, and engineers working 70-hour weeks with slide rules as their only computers. Consider the software breakthrough no one saw coming. The Apollo guidance computer had less power than a modern thermostat, yet it had to navigate 250,000 miles through unforgiving space. Programmers like Don Iles wrote code so elegant it could land on the moon with just 2 kilobytes of memory. Their secret: they treated math like poetry, distilling equations to their purest form. When Armstrong took manual control during the final descent, burning precious fuel, it was their algorithms that kept him from crashing into a field of boulders. Then there were the sacrifices etched in silence. 3 Apollo 1 astronauts perished in a cabin fire during a test, a tragedy that forced NASA to redesign every spacecraft. The Soviet Union's lunar program, shrouded in secrecy, claimed unknown lives, cosmonauts whose deaths weren't acknowledged until decades later. Even the moon bears scars of this struggle: abandoned rovers, discarded tools, and a plaque reading, "We came in peace for all mankind, resting in eternal dust." What fueled this collective obsession? Beyond geopolitics, beyond glory, there was something primal: the unshakable belief that if humanity could touch the moon, we might finally grasp our own potential. Every welder, every programmer, every technician who contributed understood they weren't just building machines, they were stitching a ladder to the stars, one painstaking innovation at a time. And when Armstrong radioed, "The Eagle has landed," it wasn't just a team's triumph, it was proof that when we unite under a single impossible dream, the cosmos bends to meet us halfway. The universe has its own heartbeat, steady, precise, and utterly relentless. In 1967, a young graduate student named Jocelyn Bell was sifting through reams of radio telescope data when she noticed something peculiar: a rhythmic pulse ticking every 1.337 seconds with atomic clock precision. At first, her team jokingly labeled it LGM-1, little green men wondering if they'd stumbled upon an alien beacon. But the truth was even stranger. Bell had discovered the first pulsar, the spinning corpse of a massive star that had died in a supernova explosion, leaving behind a city-sized cinder so dense that a teaspoon of it would weigh 1 billion tons on Earth. These cosmic lighthouses are nature's most precise clocks. As a pulsar spins, beams of radiation shoot from its magnetic poles like a lighthouse's rotating light. If those beams sweep across Earth, we detect them as pulses, some as regular as the ticking of a metronome, others wobbling slightly due to unseen planets orbiting the dead star. The Crab Nebula's pulsar, born in a supernova observed by Chinese astronomers in 1054, spins 30 times per second, while the slowest known, nicknamed the Black Widow, takes 23 seconds to complete a rotation. But pulsars aren't just celestial oddities, they're laboratories for testing the extremes of physics. Einstein's theory of general relativity predicts that massive, spinning objects should warp spacetime, creating ripples called gravitational waves. In the 1970s, astronomers found a pulsar orbiting another dense star, and over decades, they watched its orbit shrink exactly as Einstein's equations predicted energy lost to gravitational waves. It was the first indirect proof these ripples existed, decades before LIGO direct detection. Then there's their role as cosmic GPS. The Voyager probes carried pulsar maps, their unique pulse patterns acting as galactic signposts to guide any future finders back to Earth. Even today, scientists are testing pulsar-based navigation for spacecraft, using these dead stars as interstellar beacons. Perhaps the most haunting pulsar mystery lies in their eventual fate. Over millennia, their spins slow, their beams fade, yet some, like the millisecond pulsars, get a second lease on life, siphoning gas from a companion star, revving up to dizzying speeds. They're the universe's timekeepers, ticking away long after the stars that birthed them have vanished. And in their steady pulses, we find something profound. Even in death, the cosmos refuses to be silent. Black holes weren't always the celestial celebrities they are today. In 1916, when Carl Schwarzschild solved Einstein's equations and revealed their possibility, even Einstein balked at the idea. Nature doesn't play that way, he insisted. The notion of a star collapsing into an infinitely dense point, a singularity where space and time break down, seemed too bizarre to be real. Yet a century later, we've not only confirmed their existence, we've photographed one, the supermassive beast at the heart of Galaxy M87, its shadow ringed by fiery gas, a cosmic bull's eye 55 million light-years away. So how does a black hole form? Picture a massive star 10 times heavier than our Sun, burning through its fuel in a final, furious blaze. When fusion stops, the outward pressure vanishes and gravity wins in an instant. The star implodes, crushing itself smaller than a pinprick, but its gravity remains, now so intense that not even light can escape its grip. That's the event horizon, the point of no return. Cross it and every path leads inward. Time distorts like taffy. A second for you might be centuries for someone watching from safety. Then came Stephen Hawking's bombshell. In 1974, he proposed that black holes aren't entirely black. Quantum fluctuations at the event horizon, he argued, should emit faint radiation, now called Hawking radiation. Over eons, this slow leak would cause black holes to evaporate, vanishing in a final burst of energy. It was a revelation. Even these cosmic vacuums aren't eternal. But the weirdness doesn't stop there. Some theories suggest black holes could be gateways. Their singularities might warp space-time so severely that they punch through to other universes or dimensions, though anyone attempting the trip would be spaghettified by tidal forces long before arriving. Others propose holographic black holes, where all the information swallowed is encoded on their surfaces like a cosmic hard drive. Perhaps the most haunting question is this: what happens inside? The equations break down at the singularity, leaving us staring into a mathematical abyss. Some physicists think quantum gravity theories will one day rewrite the rules, revealing a cosmos where black holes birth new universes in their depths. Until then, they remain the ultimate cosmic paradox, both destroyers and potential creators, nature's most perfect prisons and its most tantalizing keys. For centuries, we could only wonder, are there other worlds like ours orbiting distant suns? That question shattered in 1995 when Swiss astronomers Michel Mayor and Didier Queloz made an announcement that sent shockwaves through science. They'd found a planet orbiting not our Sun, but another star entirely. 50 light-years away, the gas giant Dimidium, later nicknamed Bellerophon, was whirling around its star 51 Pegasi in just 4 days. This wasn't just a new planet, it was proof that our solar system wasn't unique. The cosmic dice had been rolled countless times across the galaxy. The discovery kicked open a door astronomers had been knocking on for decades. Early attempts to spot exoplanets had failed not because they weren't there, but because stars outshine their planets by billions to one. Mayor and Queloz cracked the code by watching for the subtle wobble a planet's gravity induces in its host star. That wobble, detectable in the star's light spectrum, revealed planetary dance partners otherwise invisible to telescopes. Within years, the floodgates opened. Hot Jupiter's gas giants skimming blisteringly close to their stars appeared first, defying expectations. Then came super-Earths, mini-Neptunes, and worlds stranger than fiction. Fast forward to today, and the exoplanet catalog boasts over 5,000 confirmed worlds, with thousands more candidates waiting in the wings. Kepler Space Telescope, launched in 2009, became a planet-hunting powerhouse, staring at one patch of sky for years, catching the faint dimming of starlight as planets crossed their sun's faces. Its data revealed something staggering. On average, every star in the Milky Way hosts at least one planet. That's hundreds of billions of potential worlds, an abundance no one anticipated. But the real thrill lies in the Goldilocks zone, the orbital sweet spot where liquid water could exist. Planets like Kepler 438b, a rocky world 12 light-years away bathed in gentle starlight, or TRAPPIST-17 Earth-sized siblings, 3 of which orbit in their tiny star's habitable zone. These aren't just dots on a chart, they're possible homes for chemistry that might have taken the same leap ours did. The search has grown more sophisticated. Now, telescopes like JWST analyze exoplanet atmospheres, hunting for chemical fingerprints, oxygen, methane, even industrial pollutants that could hint at life. Recent studies of K218b, a Hycean world with water vapor and possible dimethyl sulfide in its air, sparked debates. Could those molecules be biological in origin? Every discovery narrows the search, from rogue planets drifting between stars to tidally locked worlds where one side bakes in eternal daylight while the other freezes in endless night. The galaxy keeps serving up surprises. The answer to "Are we alone?" might already be hiding in data we've collected, waiting for the right algorithm, the sharp-eyed grad student, the moment when humanity finally points to a distant world and says, "There." Their home. Imagine tuning an old television to a dead channel, that static hiss filling the room. Now picture that same static coming not from your TV, but from the sky itself. That's the cosmic microwave background, the faint afterglow of the universe's birth, lingering like a whisper from 14 billion years ago. In 1965, 2 radio astronomers at Bell Labs, Arno Penzias and Robert Wilson, stumbled upon it while troubleshooting a persistent noise in their antenna. No matter where they pointed it, the static remained uniform and unchanging. At first, they blamed pigeon droppings on their equipment, but the truth was far grander. They'd accidentally tuned into the oldest light in existence, the cooled remnants of the Big Bang's fiery dawn. This cosmic fingerprint captures the universe at just 380,000 years old, a time so early, space itself was a searing plasma too hot for atoms to form. As the cosmos expanded and cooled, electrons and protons finally combined, releasing a flash of light that's been stretching ever since. What began as visible radiation has redshifted over eons into microwaves, painting the entire sky with a glow just 2.7 degrees above absolute zero. The astonishing part, that glow isn't perfectly smooth. Tiny fluctuations, warmer and cooler patches no larger than 1 part in 100,000, reveal the seeds of all cosmic structure. Those faint wrinkles are the gravitational blueprints for everything, galaxies, stars, even us. Yet the deeper we look, the stranger the story gets. The Planck satellite's ultra-precise maps show anomalies, a mysterious cold spot spanning billions of light years, and an unexpected lopsidedness in temperature distribution. Some theorists whisper of colliding universes, a multiverse imprint left in our sky. Others propose exotic physics, like primordial black holes or cosmic strings, defects in spacetime itself, stretching across the infant cosmos. Even the simplest measurements defy expectations. The universe appears slightly smoother on one side than the other, as if we're seeing the edge of something far larger. Perhaps the most profound revelation lies in what the background doesn't show. Its patterns align eerily with the distribution of galaxies today, as if destiny were written into the universe's first breath. And hidden within its subtle ripples are clues to dark matter's grip and dark energy's push forces that would shape cosmic fate billions of years later. The cosmic microwave background isn't just a relic, it's a cipher, a coded message from the dawn of time we're still learning to read. Every new telescope, every sharper map, brings us closer to understanding not just how the universe began, but how it chose to become the marvel we see today. Imagine the universe as a runaway train, its engines roaring louder as it hurtles faster into the void. That's the unsettling reality astronomers confronted in 1998 when two independent teams studying distant supernova made a discovery that upended cosmic physics. Instead of finding the universe's expansion slowing down as gravity's pull should dictate, they saw galaxies fleeing from one another at ever-increasing speeds. Something was pressing its foot on the cosmic accelerator, a mysterious force now called dark energy, making up a staggering 68% of the universe's total energy. What makes dark energy so baffling isn't just its dominance, it's how little we understand it. Einstein once proposed a similar concept, the cosmological constant, to balance his equations and keep the universe static. He later called it his greatest blunder when Hubble proved the cosmos was expanding. Yet here we are, a century later, realizing Einstein might have been right after all, just for reasons he never imagined. Dark energy behaves like an anti-gravity, not pulling matter together but stretching space itself apart. The emptier the universe gets, the stronger this repulsive force becomes, creating a feedback loop of acceleration. The implications are staggering. If dark energy's strength remains constant, galaxies beyond our local group will eventually vanish from view, their light stretched beyond detectability. The universe will grow cold and dark, with isolated islands of stars drifting in an ever-expanding void. But there's a more terrifying possibility. What if dark energy isn't constant? Some theories suggest it could intensify over time, leading to a Big Rip scenario where even atoms are torn apart as space itself shreds at an exponential rate. Yet dark energy's fingerprints are everywhere. It's etched into the large-scale structure of the cosmos, suppressing the growth of galaxy clusters. It leaves its mark in the cosmic microwave background's subtle patterns. Even the rate at which supernova dim with distance betrays its presence. The problem, no particle in the standard model explains it. Is it vacuum energy? A new fundamental field, or evidence we've misunderstood gravity entirely. The hunt for answers is reshaping astronomy. Projects like the Dark Energy Spectroscopic Instrument are mapping millions of galaxies to trace expansion's history, while the Euclid Space Telescope peers into the cosmic web structure. Each new dataset narrows the possibilities, yet dark energy remains as elusive as ever. One thing's certain, solving this riddle won't just tell us how the universe ends, it'll reveal what the cosmos is truly made of. And that's a mystery worth chasing to the edge of time itself. There's a thought experiment that keeps cosmologists up at night. What if our universe, with all its galaxies and laws of physics, is just one page in an infinite cosmic library? The multiverse hypothesis suggests exactly that. Reality as we know it might be a single bubble floating in a frothing sea of other universes, each with its own unique rules. This isn't science fiction. It's a serious idea born from the edges of string theory and quantum mechanics. Picture the early universe, a cauldron of space and time bubbling with unimaginable energy. According to inflationary theory, some of those bubbles may have pinched off, forming self-contained universes with different physical constants, places where gravity might be weaker, light faster, or where atoms never formed at all. String theory adds another layer to this cosmic tapestry. It proposes that the fundamental particles we know are just vibrations of tiny, multidimensional strings. But for the math to work, These strings need 10 or 11 dimensions to dance in far more than the 3 of space and 1 of time we experience. Where are the extra dimensions? They could be curled up, hidden from view, or existing in parallel realities we can't access. Some models suggest these hidden dimensions might host alternate universes, separated from ours by less than a millimeter, yet forever out of reach. Then there's quantum mechanics, with its dice-rolling approach to reality. Every time a particle's fate is decided decaying or not decaying, spinning up or down, the universe might split into multiple branches, each representing a different outcome. In one timeline, dinosaurs never went extinct. In another, you made that left turn instead of a right. These many worlds interpretations don't just hint at a multiverse, they demand it, with infinite versions of history unfolding simultaneously. But how could we ever test such a wild idea? Surprisingly, there are clues. If our universe ever collided with another, the crash might leave scars in the cosmic microwave background, anomalies like the mysterious cold spot. Some researchers argue could be a bruise from a long-ago multiverse encounter. Others hunt for evidence in the distribution of galaxies, looking for patterns that might betray the gravitational tug of a neighboring universe. The implications are staggering. If the multiverse is real, then every conceivable outcome exists somewhere. Somewhere, a version of you is reading this script on a planet where the sky is purple. Somewhere, the laws of physics conspired to make life impossible. And somewhere, there might be a universe so alien we can't even imagine it. This isn't just about alternate histories, it's about the very nature of existence. Are we the rule or the exception? The multiverse doesn't just expand space, it explodes our understanding of reality itself. The silence is deafening. With trillions of stars in our galaxy alone, each potentially hosting habitable worlds, the cosmos should be teeming with civilizations. So why does the universe feel so empty? This is the Fermi Paradox, the unsettling contradiction between the high probability of alien life and our complete lack of evidence for it. When physicist Enrico Fermi first posed the question, "Where is everybody?" over lunch in 1950, he wasn't just making small talk. He was pointing out a cosmic riddle that still baffles scientists today. Consider the numbers. The Milky Way contains roughly 400 billion stars, many with planets in their Goldilocks zones. Even if only 1 in a million developed intelligent life, that's still 400,000 civilizations. Given the galaxy's 13 billion-year history, some should have had ample time to colonize every corner of it. Yet our radio telescopes hear only static, and our telescopes see no megastructures or interstellar fleets. The Great Filter theory offers one grim explanation. Perhaps some catastrophic barrier, nuclear war, runaway AI, or environmental collapse wipes out civilizations before they can spread. If true, the silent sky might be a warning, but not all solutions are so dire. Maybe advanced aliens avoid primitive species like us, following a galactic version of the Prime Directive. Or perhaps they communicate in ways we can't detect, using neutrino beams or quantum entanglement instead of radio waves. There's even the haunting possibility that we're the first, that the universe, still young by cosmic standards, hasn't had time for others to rise. Then there's the zoo hypothesis, the idea that Earth is a protected wildlife preserve, deliberately left untouched, or the dark forest theory, which suggests every civilization stays hidden, fearing that any broadcast might attract predators. Each answer raises more questions. If aliens are hiding, what are they afraid of? If they're extinct, what doomed them? The paradox forces us to confront our place in the universe. Are we a fluke or an inevitability, a cautionary tale or a future empire? Until we find even a single microbe beyond Earth, the stars keep their secrets. And as we listen to the silence, we're left wondering, are we the universe's only children, or is something out there, waiting in the dark, listening back? Deep beneath the ice of Antarctica, in lakes sealed off from sunlight for millions of years, life not only survives, it thrives. These extremophiles, organisms that flourish in conditions once thought uninhabitable, are rewriting the rules of biology. If life can persist in boiling hydrothermal vents, acidic hot springs, or the crushing depths of the Mariana Trench, why couldn't it take root in the subsurface oceans of Europa or the methane lakes of Titan? Astrobiology, the study of life's potential beyond Earth, isn't just about hunting for little green beings. It's about probing the universe's capacity for chemistry to blossom into biology, no matter how alien the environment. Take Mars, our most tantalizing neighbor. Once a world of rivers and lakes, its rusty surface now hides traces of ancient water, dry riverbeds, mineral deposits, and even seasonal brine flows. The Perseverance rover, scouring Jezero crater, has already uncovered organic molecules, the building blocks of life. But here's the twist: finding these compounds doesn't mean life existed there. They could have formed through purely geological processes. The real smoking gun would be something like a fossilized microbial mat, or even better, a living organism tucked beneath the radiation-shielded soil. That's why future missions like the Mars Sample Return Campaign aim to bring pristine Martian dirt back to Earth, where labs can scrutinize it for biosignatures too subtle for rovers to detect. Then there's Europa, Jupiter's icy moon. Beneath its cracked, frozen shell lies a global ocean twice the volume of Earth's, kept liquid by tidal forces flexing its core. Hydrothermal vents on its seafloor might mirror those on Earth, where life thrives without sunlight, fueled by chemosynthesis. NASA's upcoming Europa Clipper mission will map this hidden ocean's chemistry, hunting for plumes that might spew microbial hitchhikers into space. Even Enceladus, Saturn's tiny moon, joins the fray with its own icy geysers ejecting water vapor and organic compounds, a cosmic soda fountain begging to be sampled. But life's cosmic odds aren't just about location. Timing matters too. Venus, now a hellscape of sulfuric acid clouds, may have had a temperate climate for billions of years before a runaway greenhouse effect boiled its oceans away. Did life get a foothold there before the apocalypse? Phosphine gas detected in its atmosphere, a potential biosignature, hints at lingering mysteries. Meanwhile, exoplanets like K218b, a Hycean world with water vapor and methane in its atmosphere, stretch the definition of habitable zones. The deeper we look, the more we realize life's playbook might be vaster than we imagined. Silicon-based organisms, ammonia-breathing microbes, the possibilities are as boundless as the cosmos itself. Every mission, every telescope, every lab experiment probing life's limits brings us closer to answering humanity's oldest question. In this grand, star-strewn theater, are we the only actors on the stage? The James Webb Space Telescope didn't just open a new window to the cosmos, it shattered the glass entirely. Perched a million miles from Earth, its golden honeycomb mirrors catch whispers of light from the universe's infancy, revealing galaxies so ancient they shouldn't exist. In its very first deep-field image, Webb spotted Glass Z13, a galaxy born just 300 million years after the Big Bang, a time when theorists believed the cosmos was still too young to craft such colossal structures. These primordial giants, glowing with the light of a billion newborn stars, rewrite the cosmic timeline, forcing astronomers to question how galaxies could assemble so quickly after the universe's fiery birth. But Webb's infrared vision does more than peer into the past. It strips away the veil of cosmic dust that hid stellar nurseries from Hubble's gaze. Take the pillars of creation, those iconic towers of gas where stars are born. Hubble's visible light portrait showed their silhouettes against a starry backdrop, but Webb's infrared eyes pierced straight through, exposing hundreds of hidden protostars, tiny, luminous knots nestled in the gas like fireflies in fog. Each one is a sun in the making, some still swaddled in dusty cocoons, others already blasting out jets of material that stretch light years into space. These aren't just pretty pictures, they're textbooks in motion, showing us how stars like our own emerge from chaos. Then there's the exoplanet revolution. Webb's spectrographs dissect the light filtering through distant worlds, atmospheres with surgical precision, sniffing out chemicals we once thought impossible to detect. When it analyzed WASP-39b, a scorching gas giant 700 light-years away, it found carbon dioxide, water vapor, and even sulfur dioxide, a cocktail that hints at complex atmospheric chemistry. But the real stunner came with K218b, a Hycean world orbiting a red dwarf. Webb detected dimethyl sulfide, a molecule on Earth produced only by living organisms. Could it be a sign of alien plankton? Probably not yet. But the mere possibility sends shivers down the spine of science. What's next for Webb? Perhaps it'll spot the first definitive biosignatures, oxygen and methane dancing in an exoplanet's air, the telltale waltz of life. Or maybe it'll find even older galaxies, pushing the dawn of cosmic structure closer to the Big Bang itself. Some theorists whisper it might even glimpse population, 3 stars, the universe's firstborn, forged from pure hydrogen and helium, so massive they lived fast, died young, and seeded the cosmos with the heavy elements that built us. Every photon Webb collects is a message in a bottle, tossed across time and space. And as its mirrors tilt toward new targets, distant quasars, colliding galaxies, icy moons, we're not just observing the universe. We're rediscovering it layer by layer, revelation by revelation. The cosmos has kept its secrets for billions of years. Now, at last, it's starting to talk. Neutron stars are the universe's ultimate pressure cookers, city-sized remnants of dead stars, so dense that a single teaspoon would weigh 1 billion tons on Earth. Now imagine 2 of these cosmic wrecking balls spiraling toward each other, locked in a gravitational death spiral. When they finally collide, the explosion is so violent it momentarily outshines entire galaxies, forging gold, platinum, and other heavy elements in a fireball of unimaginable heat. This isn't just a spectacle. It's the universe's way of minting the very metals that make up your wedding ring or smartphone. The process, known as a kilonova, is a masterclass in cosmic alchemy. As the neutron stars merge, their crushing gravity rips them apart, ejecting neutron-rich material into space at nearly the speed of light. In this maelstrom, atomic nuclei capture free neutrons faster than they can decay, rapidly building heavier and heavier elements in a process called rapid neutron capture, or the R process. Within seconds, enough gold is created to outweigh entire planets. Every time you hold a piece of jewelry, you're holding stardust forged in one of the most violent events in the universe. But the drama doesn't stop there. These collisions send ripples through space-time itself, gravitational waves that stretch and squeeze the fabric of reality. In 2017, detectors LIGO and Virgo caught the faint echo of such an event, GW 170817, marking the first time humanity had witnessed a neutron-star merger through both gravitational waves and light. The data revealed something astonishing. The collision spewed out a cloud of heavy elements equivalent to several hundred Earth masses. Suddenly, we had a front-row seat to the universe's foundry, watching as it crafted the very building blocks of planets and life. Here's the twist: without these cataclysmic smash-ups, life as we know it might not exist. Elements like uranium, iodine, and even the iron in your blood were either born in the hearts of dying stars or forged in neutron star collisions. The cosmos doesn't just create, it recycles. The gold in your earrings might have once been part of a star that died billions of years ago, only to be hurled into space by a kilonova, eventually finding its way into a nebula that birthed our solar system. Yet mysteries remain. Why do some neutron star collisions produce more gold than others? Could these events also create elements we've never seen before? And what happens to the remnants? Does the collision leave behind a black hole or an even more exotic object? Every new detection peels back another layer, revealing a universe far more dynamic and interconnected than we ever imagined. So the next time you glance at the night sky, remember, the stars aren't just distant lights. They're the architects of everything, including you. Somewhere beyond the veil of the Milky Way's dust, in the direction of the constellations Centaurus and Hydra, the universe is playing a game of tug-of-war, and we're on the losing team. Meet the Great Attractor, a gravitational anomaly so powerful it's dragging entire galaxies, including our own, toward it at over 14 million miles per hour. For decades, this cosmic heavyweight remained hidden, its presence betrayed only by the peculiar motion of galaxies that refused to follow the universe's expansion as expected. Like a phantom hand in the dark, it pulls without revealing its face. At first, astronomers assumed it must be a colossal supercluster, a dense knot of galaxies with gravity strong enough to bend the paths of neighboring celestial bodies. But when they peered deeper, the math didn't add up. The Great Attractor's influence stretches far beyond what visible matter could explain. Even the massive Norma cluster, sitting near the center of this gravitational vortex, can't account for the sheer scale of the pull. There's something else lurking there, something unseen and unexplained. Here's where the mystery deepens. To study the Great Attractor, scientists had to contend with an ironic obstacle: our own galaxy. The Milky Way's dusty disk blocks visible light from the very region they needed to observe, creating a cosmic blind spot dubbed the zone of avoidance. It's like trying to map a mountain range while standing in a fog bank. Only with infrared and radio telescopes could researchers pierce through the obscuration, revealing hints of massive structures, galaxies upon galaxies huddled in the darkness. But the plot thickens. Recent surveys suggest the Great Attractor might not even be the main player in this cosmic drama. Behind it lies an even larger gravitational beast, the Shapley supercluster, a sprawling metropolis of galaxies over 400 times the mass of the Milky Way. Some theorists propose we're caught in a celestial river, with the Great Attractor as a mere waypoint in a far grander current flowing toward Shapley's unimaginable bulk. Yet even this explanation feels incomplete. The universe's largest structures, filaments of galaxies strung across billions of light years, exert their own tidal forces, complicating the tug-of-war. Add dark matter's invisible web into the mix, and the puzzle grows more tangled. Could the Great Attractor be a knot in this cosmic net, a place where dark matter's threads converge? Or is it a sign of something stranger, a flaw in our understanding of gravity itself? One thing's certain: the Great Attractor reminds us how little we truly see. For all our telescopes and probes, the cosmos still holds cards close to its chest. Every time we think we've mapped the universe, it reveals another layer, another secret. The void doesn't just call, it whispers in a language we're only beginning to decipher. Time doesn't just pass in space, it bends, stretches, and warps in ways that defy our everyday experience. Picture an astronaut orbiting Earth at 17,000 miles per hour. According to Einstein's theory of relativity, their clock ticks ever so slightly slower than an identical clock on the ground. This isn't science fiction, it's measurable. After 6 months aboard the International Space Station, astronauts return home having aged about 0.007 seconds less than the rest of us. Tiny, yes, but proof that time itself is malleable, shaped by speed and gravity in a cosmic dance. Now crank the dial to extremes. Near a black hole where gravity twists space-time like taffy, time doesn't just slow, it grinds to a near halt. Imagine a spacecraft hovering just outside the event horizon. To distant observers, its crew would appear frozen, their movements stretched into infinity. Yet for the astronauts themselves, time flows normally. They could descend toward the black hole, cross the point of no return, and experience mere minutes while centuries pass back on Earth. This is relativity's cruelest trick. The universe has no master clock. Every observer carries their own personal ticking, woven into the fabric of their journey. So what does this mean for future deep space travelers? A voyage to Proxima Centauri, our nearest stellar neighbor, would take over 4 years as measured from Earth. But for a crew traveling at 90% light speed, the trip might feel like just 18 months. The faster you go, the more time contracts around you, a phenomenon called time dilation. Colonists bound for distant stars could arrive to find their homeworld transformed, their loved ones long gone while they've barely aged. Time becomes not just a measurement, but a tangible cost of exploration. Yet the weirdest implications lie beyond speed. Orbit a neutron star, and your GPS would need constant updates. Time there passes 30% slower than on Earth. Even flying eastward at commercial jet speeds makes your watch lag behind ground clocks by nanoseconds, a quirk airlines must account for to keep navigation precise. The universe whispers these truths in subtle ways, reminding us that time is never absolute. Here's the twist: time dilation isn't just a hurdle, it's a tool. Future missions might harness it to reach farther than physics seems to allow. A generation ship traveling at near light speed could span galaxies within a crew's lifetime. Or perhaps we'll discover ways to manipulate spacetime itself, bending the rules as we once bent the seas to our will. Until then, every tick of the cosmic clock reminds us, to journey among the stars is to dance with time itself, and the music plays differently for every traveler. Oumuamua didn't announce its arrival, it simply appeared, a silent, shadowy visitor slicing through our solar system in October 2017, moving too fast to be tied to our sun's gravity. Astronomers at the Pan-STARRS telescope in Hawaii spotted it first, its name translating to "scout from the distant past" in Hawaiian. But this was no ordinary space rock. Its shape alone defied expectations, elongated like a cosmic cigar, tumbling end over end, with dimensions estimated at roughly 800 meters long and only 80 wide, a shape never before seen in our celestial neighborhood. What made Oumuamua truly extraordinary was its origin. Calculations of its trajectory revealed it wasn't from around here. This was the first confirmed interstellar object ever detected, a wanderer from another star system passing through ours like a ship in the night. Its speed, 96,000 miles per hour, was far too great to have been captured by the sun's pull. It had come from somewhere else, and it was leaving just as quickly. Then came the anomalies. As Oumuamua hurtled away, telescopes noticed something bizarre. It wasn't slowing down as expected. Most objects coasting through space obey gravity's rules, but Oumuamua seemed to be accelerating slightly, as if pushed by an unseen force. Comets often exhibit similar behavior when sunlight vaporizes their icy surfaces, creating a faint thrust. But Oumuamua showed no visible coma, the glowing halo of gas and dust typical of comets. No tail, no outgassing, nothing. So what was propelling it? The mystery sparked wild theories. Harvard astronomer Avi Loeb famously suggested the possibility, however slim, that Oumuamua could be artificial in origin, perhaps a light sail from an alien civilization drifting between the stars. The idea made headlines, but most scientists remained skeptical. Nature, after all, has a way of surprising us without invoking extraterrestrial engineers. Alternative explanations emerged. Maybe Oumuamua was a fragment of a Pluto-like world, rich in nitrogen ice that vaporized invisibly as it neared the sun. Or perhaps it was a cosmic dust bunny, a porous aggregate of interstellar materials so light and fragile that sunlight alone could nudge it forward. The truth is, we may never know. By the time Oumuamua was identified, it was already racing out of sight, too distant for further study. It left behind a trail of questions and a tantalizing glimpse into the diversity of objects lurking between the stars. If Oumuamua was just the first, how many more interstellar interlopers slip past unnoticed every year? Current estimates suggest at least one such visitor cruises through the inner solar system annually, unseen and unremarked. Future telescopes like the Vera C. Rubin Observatory promise to catch them earlier, giving us a closer look at these nomads from distant suns. Oumuamua's legacy isn't just about one strange object. It's a reminder that the universe is far stranger and more dynamic than we often assume. The cosmos doesn't just contain stars and planets. It's filled with unseen travelers, oddities that defy categorization, and perhaps even artifacts of civilizations we've yet to meet. Every time we peer into the dark, we're reminded we've only just begun to explore, and the next visitor could be even more extraordinary. The Kuiper belt stretches beyond Neptune like a frozen archive, its icy bodies untouched by time or the sun's warmth. This isn't just a scattering of space rocks, it's a preserved relic of the solar system's earliest days, a cosmic deep freeze where the raw ingredients of planets have lingered unchanged for billions of years. Pluto, once the ninth planet, now reigns as the belt's most famous resident, but it's far from alone. Hundreds of thousands of objects, some no larger than a city block, others rivaling Pluto in size, drift in this twilight zone, their orbits tracing ghostly paths through the outer dark. What makes these frozen worlds so extraordinary is their purity. Unlike the inner planets, battered by collisions and transformed by geological upheaval, Kuiper belt objects are time capsules. Their surfaces, laced with methane, nitrogen, and water ice, hold chemical fingerprints from the solar nebula, the same swirling cloud of gas and dust that birthed the Sun and all its planets. When NASA New Horizons spacecraft zipped past Pluto in 2015, it didn't just snap breathtaking photos of heart-shaped glaciers. It revealed a world far more dynamic than anyone predicted. Cryovolcanoes spewing icy slush, shifting nitrogen glaciers, and even hints of a subsurface ocean suggested that Pluto was no inert ice ball, but a geologically active world with secrets to share. The surprises didn't stop there. Deeper in the belt, dwarf planets like Haumea spin so fast they're stretched into oval shapes, while Make's surface glistens with frozen methane that acts like cosmic sunscreen, reflecting sunlight into the void. Then there's Arrokoth, the most distant object ever visited by a probe. Nicknamed Ultima Thule before its official naming, this bi-lobed snowman-shaped body offered a jaw-dropping revelation. It's essentially two separate objects that gently merged in the solar system's infancy, preserved in pristine condition. Its undisturbed structure is like stumbling upon a fossilized embryo of planet formation, capturing the exact moment when tiny particles began clumping into larger bodies. But the Kuiper belt's greatest gift might be hiding in its shadows. Some astronomers suspect a massive, undiscovered world, dubbed Planet 9, could be lurking far beyond the known belt, its gravity subtly herding smaller objects into odd orbits. Whether this phantom planet exists or not, the belt's outer reaches are a frontier ripe for exploration, where every new discovery peels back another layer of our solar system's origin story. One thing's certain, these icy sentinels aren't just leftovers. They're storytellers whispering clues about how stardust became worlds and how a chaotic young solar system settled into the order we know today. The next time you gaze at the night sky, remember out there in the cold and dark, frozen chapters of our cosmic history are waiting to be read. The sun has been Earth's unwavering companion for 4.6 billion years, bathing our planet in the steady glow that nurtured life's first fragile steps. But this cosmic partnership has an expiration date, one written in the laws of physics. In about 5 billion years, the sun will exhaust the hydrogen fueling its core, triggering a violent transformation. As fusion falters, the star's outer layers will balloon outward, swallowing Mercury and Venus whole before stretching its fiery fingers toward Earth. Oceans will vaporize, mountains melt, and the very rock beneath our feet dissolve into the star's expanding atmosphere. Our world, the cradle of humanity, will become a footnote in the sun's death throes. This isn't just a slow-motion disaster, it's a paradox of celestial inevitability. The same nuclear fires that made life possible will one day erase it. Yet even as the sun bloats into a red giant, its core will collapse into a dense, Earth-sized ember called a white dwarf, glowing faintly with leftover heat for trillions of years. The inner solar system will become a graveyard of scorched worlds, while the surviving gas giants and their moons might find themselves suddenly warmed by the dying star's temporary embrace. Europa's frozen ocean could thaw, Titan's methane lakes might churn with new chemistry, and who knows what dormant possibilities could awaken in those distant outposts. So what becomes of us? 5 billion years is an almost incomprehensible span, longer than all of complex life's history on Earth. If humanity, or whatever we evolve into, still exists by then, interstellar migration won't just be an option, it'll be a necessity. Imagine generation ships coasting toward newly born stars, or civilizations harnessing black holes for energy to power artificial worlds. Some might choose to stay, building Dyson swarms to capture the white dwarf's lingering energy, while others could upload consciousness into machines unshackled from biological limits. But here's the twist: the sun's death isn't just an ending, it's a cosmic wake-up call. Every star in the sky will eventually face this fate, some far sooner than ours. The universe is a temporary stage, and if life wishes to endure, it must learn to outgrow its cradle. That's the silent lesson written in the sun's fiery future. Survival isn't about clinging to one world, but embracing the boundless possibilities beyond it. The clock is ticking, but for a species that's already touched the moon and mapped the genome, 5 billion years is more than enough time to rewrite its destiny. Imagine Earth not just as a rock teeming with life, but as a vast, breathing entity, its oceans, atmosphere, and geology working in concert like the cells of some planetary-scale organism. This is the heart of the Gaia hypothesis, a radical idea first proposed by chemist James Lovelock and biologist Lynn Margulies in the 1970s. They suggested that living things don't merely adapt to their environment, they actively shape it, creating feedback loops that maintain conditions suitable for life. Take our oxygen-rich atmosphere. It's not just a lucky accident, but the product of billions of years of photosynthesis, with organisms tweaking the mix to keep temperatures stable. Even ocean salinity stays in check, as if some invisible hand were adjusting a cosmic thermostat. Now stretch that idea across the cosmos. If Earth can function like a self-regulating system, why couldn't other worlds? Mars, with its rusty deserts, might once have harbored microbial communities that altered its ancient rivers and air. Venus, now a scorching hellscape, could have hosted a fleeting Gaian balance before runaway greenhouse gases tipped it into chaos. And then there's Titan, Saturn's moon, where methane cycles through lakes and clouds like water does here, a hint that non-water-based life might forge its own planetary scale equilibriums. The line between a living world and a sterile one starts to blur when you consider how deeply biology and geology intertwine. Critics argue Gaia gives too much agency to life, as if Earth were somehow aware of its own balance. But newer models show how simple chemical and biological processes can create self-regulating systems without any grand design. Volcanoes belch carbon dioxide, plants absorb it, and rocks lock it away, a dance of feedbacks that, over eons, keeps the climate in check. It's not purposeful, but the effect is the same, a planet that tends to stabilize itself, at least until external shocks like asteroid impacts or human pollution overwhelm the system. The implications are staggering. If Gaia-like processes are universal, then habitable planets might not be rare gems, but resilient systems that actively maintain their own suitability for life. A world with the right starter ingredients could bootstrap itself into stability, fostering ever more complex organisms. Or perhaps we're seeing the opposite, planets that failed to self-regulate, like Mars, their biospheres collapsing as conditions spiraled out of control. Either way, the cosmos might be full of worlds that aren't just alive with life, but alive in a deeper, more interconnected sense where the boundary between organism and environment dissolves into something far stranger. After all, if a planet can breathe, what other metaphors might we one day replace with reality? Picture this, the entire observable universe, all its galaxies and voids, crammed into a space smaller than a single atom. Now imagine that unfathomably dense speck suddenly stretching to the size of a grapefruit in less than a trillionth of a second. This isn't science fiction, it's cosmic inflation, the wildest roller coaster ride the universe ever took. In that fleeting moment, space itself expanded faster than the speed of light, smoothing out wrinkles and planting the seeds for everything we see today. The puzzle, why inflation happened at all. The leading theory points to a mysterious energy field called the inflaton, a sort of cosmic spring loaded with potential energy. When this field rolled down to a lower energy state, it unleashed a repulsive gravity effect, making space push itself apart violently. Think of it like a ball perched on a hill. While it sits there, nothing happens, but once it starts rolling, the energy releases in an unstoppable chain reaction. Only here, the hill was a quantum field, and the ball's descent birthed the cosmos. Here's where it gets stranger. Inflation explains why the universe looks so uniform in every direction. Without it, opposite edges of the cosmos would never have had time to even out their temperature, yet the cosmic microwave background shows they match almost perfectly. It's like walking into a room where 2 cups of coffee, poured miles apart, are somehow the exact same temperature. Inflation solves this by suggesting these regions were once cozy neighbors before being flung apart in that initial expansion. But the smoking gun evidence came in 2014, when the BICEP 2 telescope appeared to detect primordial gravitational waves, ripples in spacetime from inflation's violent stretching. Though later deemed inconclusive, the hunt continues. New experiments like the Simons Observatory scan the cosmic microwave background for the faint swirl patterns these waves would leave, like fingerprints on the universe's oldest light. The craziest part, we may never know what kicked off inflation itself. Some theories suggest it was a quantum fluctuation, a random burp in the fabric of reality. Others propose our universe is just one bubble in a frothing multiverse, where inflation starts and stops unpredictably across infinite realms. Whatever the answer, those first moments remind us, the universe didn't just begin, it exploded into being with a creativity we're still struggling to comprehend. Quantum mechanics and general relativity are like two brilliant minds speaking different languages, both undeniably correct in their domains, yet utterly incompatible when forced to converse. On one hand, quantum mechanics paints reality as a probabilistic dance of particles, where electrons exist in multiple places at once until observed. On the other, Einstein's relativity describes gravity as the smooth curvature of spacetime, where planets and stars move along elegant geodesics. But when these frameworks collide, like at the center of a black hole or during the universe's first moments, the equations explode into nonsense. The search for a theory of quantum gravity isn't just academic, it's a desperate scramble to understand reality's deepest layers. Enter string theory, the boldest attempt to bridge this divide. Imagine every particle isn't a point but a tiny, vibrating string. The pitch of these vibrations determines whether the string manifests as an electron, a quark, or even a graviton, the hypothetical carrier of gravity. The math is breathtakingly complex, requiring 10 or 11 dimensions curled up into shapes called Calabi-Yau manifolds, so tiny we'll never perceive them. For decades, string theory dominated the conversation, promising a theory of everything, but cracks emerged. The theory predicts a near-infinite number of possible universes, making testable predictions nearly impossible. And without experimental proof, is it physics or philosophy, loop quantum gravity offers a radically different approach. Instead of strings, it proposes space-time itself is woven from finite, interlocking loops, a fabric of tiny quantum stitches. Picture the universe as a vast network of relationships where gravity emerges from these discrete connections. The math avoids infinities that plague other theories, even suggesting black holes might not have singularities at their cores. But like string theory, it struggles with experimental validation. How do you test something operating at scales a billion times smaller than an atom? Meanwhile, in labs worldwide, physicists are probing gravity's quantum nature through ingenious experiments. Some hunt for gravitons in the faint whispers of gravitational waves. Others cool microscopic objects near absolute zero, watching for quantum behavior in objects massive enough to bend spacetime. There's even the audacious idea that gravity isn't fundamental at all, but an emergent phenomenon like temperature arising from atomic motion. The stakes couldn't be higher. Unifying these frameworks might reveal why our universe exists at all, or whether others lurk beyond our cosmic horizon. It could explain the Big Bang's true nature, or whether time itself is an illusion. Until then, every failed experiment, every elegant equation that collapses under scrutiny, brings us closer to rewriting the rules of reality. The universe isn't holding back, it's waiting for us to ask the right question. Mars gleams like a rusty jewel in the night sky, a world within reach, but as we blueprint its first cities, we must confront an uncomfortable truth. The cosmos isn't a blank slate for humanity's unchecked ambitions. The moment we plant flags on distant soil, we inherit responsibilities far heavier than any spacesuit. Who decides the rules when nations and corporations race to mine asteroids or claim lunar real estate? The Outer Space Treaty of 1967 declared celestial bodies the province of all mankind, forbidding national appropriation. Yet today, private companies like SpaceX and Blue Origin operate in a legal gray zone where exploration blurs into exploitation. Imagine a future where Martian water, a lifeline for colonists, is cornered by a single entity. or where lunar helium-3 mines become the new oil fields, sparking off-world conflicts. The stakes aren't just about profit, they're about preventing the cosmic repetition of Earth's colonial scars. But ownership is only the first hurdle. Consider planetary protection the ethical imperative to avoid contaminating other worlds with earthly microbes. Europa's subsurface ocean or Mars' briny streaks might harbor fragile alien life, yet our rovers and boots could inadvertently smother them. The reverse risk is equally chilling. What if we bring back something hazardous? NASA Apollo astronauts quarantined after touching moon dust, but today's sample return missions demand stricter protocols. This isn't sci-fi paranoia, it's acknowledging that we're no longer just visitors. We're potential disruptors of ecosystems older than multicellular life itself. Then there's the human cost. Early Martian settlers will face brutal conditions, radiation, isolation, and dependence on fragile life support systems. Will they be pioneers or prisoners, governed by corporate contracts that prioritize productivity over well-being? The Antarctic research stations, often cited as analogs, offer cautionary tales. Mental health crises flare in confined, extreme environments. Add the impossibility of quick rescues. Mars is 8 months away on a good day, and ethical oversight becomes non-negotiable. Should children be born in off-world colonies, where lower gravity might alter their biology irrevocably? These aren't engineering puzzles, they're moral quandaries that demand inclusive dialogue, not just boardroom decisions. Perhaps the greatest test lies in our vision for spacefaring civilization. Will we export Earth's inequalities, with luxury orbital hotels floating above struggling lunar labor camps? Or can we craft interstellar societies rooted in cooperation, sustainability, and reverence for the environments we enter? The choices we make today, from drafting space constitutions to designing closed-loop habitats, will echo across millennia. The stars don't belong to us. But if we're wise, we might earn our place among them. From ancient stargazers tracing constellations in desert sands to modern physicists unraveling the quantum fabric of space-time, humanity's celestial journey has been one of relentless curiosity and humbling revelation. Every time we peel back a layer of cosmic mystery, whether it's the fiery birth of stars or the ghostly whisper of dark matter, we don't just uncover new truths about the universe, we rediscover ourselves. Those Babylonian astronomers etching eclipse predictions into clay tablets, Galileo risking heresy to prove Earth moved around the sun, and Katherine Johnson calculating orbital trajectories with pencil and paper, they weren't just solving puzzles. They were stitching together a new understanding of where and what we are in this vast, shimmering tapestry. Consider how our cosmic address has expanded over millennia. Once we believed Earth stood motionless at the center of creation. Then we became a speck orbiting an average star in the Milky Way suburbs. Now we know our galaxy is just one among 2 trillion in the observable universe, drifting in a web of dark matter we can't even see. With each scale shift comes both awe and existential vertigo. What does it mean to be temporary inhabitants of a pale blue dot in an ever-growing cosmic arena? Yet there's profound beauty in this perspective. Every atom in our bodies was forged in stellar furnaces or scattered by neutron star collisions. We're not just observers of the cosmos, we're its conscious embodiment, stardust that learned to wonder about itself. The most thrilling realization, this story is nowhere near finished. Right now, telescopes are capturing light from galaxies so distant their stars died eons ago. Underground labs hunt for dark matter particles that might rewrite physics. AI sifts through radiostatic for signs of intelligence beyond Earth. And somewhere, perhaps, a young student is staring at the night sky with the same burning questions that gripped Ptolemy and Hubble, questions that will propel humanity's next great leap into the unknown. So here's your invitation. Keep looking up, not just with telescopes, but with imagination and courage. Share which cosmic mystery captivates you most: the enigma of black holes, the search for extraterrestrial life, or the riddle of why the universe exists at all. Hit subscribe to join us as we chase these questions across the frontiers of space and time, because the universe isn't just out there, it's unfolding within us, one revelation at a time. And the next chapter, it's written in the stars, waiting for curious minds to turn